Hello and welcome back. Summations like we saw in the last video, example 2, are called Riemann sums. So the example was 1 over n squared times 1 over n plus 2 over n squared times 1 over n and so on. We wrote it using this compact sigma notation, I over n squared times 1 over n. So this is called a Riemann sum. It's in this case, the sum of the areas of all those approximating rectangles. Now, if the rectangles have the same widths, like they all did here, 1 over n, then the general Riemann sum can be written like this. It's the sum as I goes from 1 to n of f of x sub I star times delta x. X sub I star here is just representing any x value inside of each of the subintervals. So in our example, we used right endpoints. Now, if we had to calculate the right endpoints using a formula, this would be it. X sub I star we could calculate as being a, which is the starting x value of your interval, plus I times delta x, where delta x gives you the width, delta x represents the width of each rectangle, and it's calculated by b minus a over n. So f of x sub I star is giving you the height of each of the rectangles. You're doing a height times width calculation for the area of each of the rectangles. Let's take a look at example 2 before we go on. Let's jump back up to example 2 to see where this new notation would appear in our example. So let me choose a color. It's always the hardest part. I'll choose that one there. So the rectangle widths are delta x. So in this case, delta x would be 1 over n. On the picture, you can see delta x right here. Here's delta x, here's another delta x, and so on. The width of each of these subintervals are delta x, or in other words, the width of the rectangles are delta x. Then the x sub I star we can find right here. So this is x sub I star. It was I over n. These were the x values that were the right endpoints because we chose to use sample x values that were the right endpoints. But they didn't have to be. We could have chosen midpoints, in which case the x sub I stars would look a little bit different, or left endpoints, and they would look maybe slightly different. If we wanted to calculate the x sub I stars using that formula, which was a plus I delta x, it would look like this. A is 0. This is like your A right here. This is like your B. A is 0. I is I. And delta x we calculated as 1 over n. So you get I over n. So I over n gives you a formula for the x values that you're going to plug in to get your heights of your rectangles. You're going to plug those x values into the function to get the heights of your rectangles. So that's how that new notation ties in with that example 2 that we just did. Here's a general function, a different one that just looks like a random function. And you can see that here are some of the x values that start and end each of the subintervals. Let's say we look at that ith subinterval, so the one that goes from x sub I minus 1 to x sub I, would be the ith subinterval. Well, x sub I star would be somewhere around here. It looks like we're using midpoints to calculate the heights of each of these rectangles. So x sub I star would be, in this case, right about here. X sub I star. Looks like it's the midpoint. Now f of x sub I star is giving us the height of this rectangle. Here's f of x sub I star in the picture, just for that one rectangle. And then delta x is, use a different color for delta x. Delta x is the width of that rectangle. Now you can calculate that as it mentions above, right here, by calculating b minus a over n. And that's what you can do. You just do that calculation once, like we did, and we got 1 over n in example 2. You do that calculation once, and then you know the width of all of the rectangles. But there is a way to generalize this even more. If the rectangles have different widths, so if you take your interval and you chop it up into a number of subintervals, but each subinterval has a different width, some are small, some are big, then you can write an even more general version of the Riemann sum. It looks something like this. The only difference is now the delta x, instead of being the same delta x for every single rectangle, it's now subscripted with an I, saying that these could be different. The delta x sub 1 might be different from the delta x sub 2. They could be the same, but they could also be different. So that's the difference between this version of the Riemann sum and then the one that we were looking at before. We're not going to use this one in this class. I just mentioned it for interest. And I also want to mention for interest that no matter what each rectangle width is, so no matter what the delta x sub i's are, as long as the maximum rectangle width, which is called the norm of all the delta x sub i's, approaches 0 as n approaches infinity, as you use more and more of those rectangles, as long as the biggest rectangle width is shrinking down to 0, then all the rest of the rectangle widths will shrink down to 0, and the limit of those sums of the areas of the rectangles is still going to equal the area under the curve. Now, one thing you might be looking at is saying, why do I keep saying net area here? Well, the reason for that is note number 2. Rectangles below the x-axis are going to be counted as a negative area in the summation. So, as an example, these subintervals, if we look at the rectangle that's raised to the curve for that subinterval, for example, well, if we're plugging in the midpoint, it would look like this. We would get a negative function value. If we plugged in this x value into the function, it would be a negative function value. So that negative function value times the delta x, which is a positive value, when you multiply those together, you're going to get a negative number. So that negative number is representing a signed area. So it's a negatively signed area for that rectangle. So when we talk about the area under a curve, what we really mean is the signed area between the curve and the x-axis, where any place that the curve is above the x-axis, where the function values are positive, will be counted as positive area. And any part where the function falls below the x-axis and gives you negative function values is going to be signed a negative area. And so a negative area and a positive area could cancel each other out when you add them together. So a quick example would be if you took the sine x function across its period, then area above the x-axis is going to be positive, area below the x-axis will be negative, and because of the symmetry of sine, we would say that the net area, this is sine x, would equal 0. This is the net area from 0 to 2 pi, just that one period of sine. So if we calculated the net area, or we would, the quote unquote the area under the curve, which is really the net area that we mean, then it would be 0 in this case because of that negatively signed area below the x-axis. Great. So again, the different width rectangles we're not going to look at. Our rectangles are all going to have the same width, so we don't have to really worry about this this first note and this little note about the delta x sub I. But we do have to be concerned about knowing that we're actually computing the net area. That's how negative function values are handled. Now we're going to use the integral symbol, it turns out, which is adding to the mystery, to represent the infinite sum of these infinitely thin rectangles. The infinite sum of the areas of these infinitely thin rectangles. So this calculates the true area under the function across our interval, And that true area under the function from a to x equals a to x equals b, we're going to represent using this integral notation. Now the difference between the integral notation that we saw last time in packet 19 and now is that we have these numbers right here on the bottom and on the top of the integral. They're not exactly on the bottom and the top, they're a little bit off to the right. But they're the lower limit and the upper limit of integration. In fact, I'm going to write that right here. A is the lower limit of integration. And B is the upper limit of integration. This together is the interval over which you're computing the net area. So on a picture, it would look something like this. Here's A, here's B, here's maybe your function, and you're trying to find the area under that curve from A to B. That's what we're looking at. So the area under that curve from A to B is going to be represented as this integral from A to B of f of x dx. And this kind of integral is called a definite integral. You can think it definitely has those limits of integration, that new stuff. It's called a definite integral. And you can read it as like this: the integral from A to B of f of x dx. That's how you can read this right here. The integral from A to B of f of x dx. F is given the name integrand. It's what we could have called f back in packet 19 as well. It's called the integrand. And the variable that you use here doesn't really matter. You can use the x as your variable, you can use t as your variable, or u as the variable. As long as the function is the same and your limits of integration are the same, then all of these are going to calculate to the same area. In fact, the x and the t and the u are sometimes called dummy variables because it doesn't matter which one you use here. X, t, and u are called dummy variables. Now this theorem is talking about when a function is going to be integrable, when you can actually evaluate the area under a function from A to B. And it basically says as long as f is continuous over the interval from A to B, with possibly a finite number of jump discontinuities, so you could jump up a little bit, as long as there's a finite number of them, then the integral from A to B of f of x dx exists. And so f is said to be integrable over the interval from A to B. In other words, you can integrate f from A to B as long as f is continuous over that interval from A to B with possibly a finite number of jump discontinuities. If there is a jump discontinuity, what you can do is break up your integral into two integrals, one for the first part and then one for the second part, split up by where that jump discontinuity is, or more than one if you have more than one. All right, a few properties of definite integrals. One is that if you flip the limits of integration, so flip the a and the b, so see a is on the top here, and then now it's on the bottom, b is on the bottom, it's on the top now. That flips the sign of your delta x calculation from either positive to negative or negative to positive, which will flip the overall sign of your integral. So when you think flipping the limits of integration flips the sign of the delta x, that's going to flip the sign of your integral. For number 2, we're integrating from a to a of f of x dx. Well, a to a is not really much of an interval. In fact, you could say the interval width there is just 0. So if you were calculating delta x, you'd have b minus a, which is a minus a in this case, which is 0 over n. And so delta x would be 0. You wouldn't have any interval to speak of. So there's not really an area under that curve. We can say that this integral is going to compute to 0 because our interval width is 0. The third property says you can pull constants out of definite integrals. That kind of makes sense. Like, if the definite integral is defined as the limit as n approaches infinity of the sum of the areas of these rectangles, well, if there's a constant in front of the function, that can come out of the summation notation. So out of the summation, you can factor it out, and then you can pull it out of the limit because there's a property that says you can pull constants out of limits. So you can pull it all the way out, which would say that you could pull it out of the definite integral. Similarly, definite integrals distribute across addition and subtraction because sigmas and summations and limits also distribute across addition and subtraction. Now, this fifth property is kind of specific to definite integrals. It says that the integral from a to b plus the integral from b to c is going to be equal to the integral from a to c. Or in terms of area, the area under the curve from a to b plus the area under the curve from b to c equals the area under the curve from a to c. Now you can say that, but having a picture is definitely worth 1,000 words here. Here's a, here's b, and here's c. And here's some function, f of x. So what this says is that the area under the curve from a to b plus the area under the curve from b to c is going to equal the area under the curve from a to c. And that just makes sense from looking at the picture. It's just area addition. The sum of these two smaller areas, of course, is going to be the sum. Is going to be equal to the sum of the total area of the bigger area. I don't know what I just said. Anyway, just look at the picture. All right. So property 6 says that the integral, so the area under the curve from a to b, can be trapped between or bounded by these two expressions. And I think it helps here again to draw a picture. So here's a picture of the right expression, the expression that's on the right. On the left, I got my rights and left switched around. Here's a picture of what it looks like on the left. Draw a little function. And what we're looking at is this area under that curve from a to b. That's what's in the middle. Now the minimum function value, so min f, this min f means the minimum function value on that whole interval. And as we trace the curve, it looks like the smallest function value is happening right here. So the minimum function value is something like that, whatever that is, whatever that y value is. So if we take that minimum function value and we multiply it by b minus a, well, b minus a is just the length of the interval. So what we can do is imagine this as the area of the rectangle that's under the curve. So it's the area of that rectangle under the curve. That's what that min f times b minus a is computing. This min f is giving you the height of the rectangle, and the b minus a is giving you the length of this rectangle, or the width of the rectangle if you want to use the same terminology that we used before. So that's giving you like a lower bound for what the area under this curve could be. On the opposite side, on the right side, we get an upper bound. So I'll try to draw the same picture. So here, if we look at the maximum function value, that's happening right around here at the top. If we take that maximum function value, which is the height of this rectangle, and multiply it by b minus a, which is the width of the rectangle, that gives you the maximum possible area of under the function. It's actually an overestimate. In fact, you can consider the first picture to be the lower sum using one rectangle, and then the picture on the right is like the upper sum using one rectangle. So this is going to give us an underestimate on the left and then an overestimate on the right. So the actual area is going to fall somewhere in between. That's what the sixth property is saying. Now the seventh property says that if you've got the function values of f greater than or equal to the function values of g on the entire interval from a to b, then the area under f is going to be bigger than or equal to the area under g. That's just because the function values are higher, so it's going to be bigger area. It's going to be more area. Let's draw a little picture of that. Let's say f is up here and g is down here. Well, the area under f is definitely going to be more than the area under g. Just because f is higher than g. So that property is kind of like common sense when you look at a picture. Let's use some of these properties in example 3. I'm not going to use all of them, but just get a flavor for how you could use some of them. So example 3 says, suppose that the integral from -1 to 1 of f of x dx is 5, and the integral from 1 to 4 of f of x dx is -2. Remember that areas under these curves can be signed negative because we're really talking about net area. So this means that under this on this interval from 1 to 4, the function has got to fall below the x-axis somewhere. And we don't know what the function is, what the expression is for this function, or even what it looks like. But we know that the net area from 1 to 4 of f of x is going to be -2. And then lastly, the integral from -1 to 1 of h of x is equal to 7. So this is the area under the h of x function. So the first thing is we're asked to find the area, or the integral from 4 to 1 of f of x. Now that's very similar to this other integral that we saw from 1 to 4, but the limits of integration are flipped around. Well, we know how to deal with that. If we flip the limits of integration, that flips the sign of the integral. And since we already know the integral from 1 to 4 of f of x is -2, we're going to get the negative of -2, which is +2. For the next part, we have the integral from -1 to 1 of 2 times f of x plus 3 times h of x. Now we know by those properties that we just discussed, the integral will work its way, it'll distribute across the plus, and we can pull out the constants, the 2 and the 3, so it basically works its way into the f of x and the g and the h of x, like this. 2 times the integral from -1 to 1 of f of x dx. Don't forget the dx. It's like an integral sandwich, remember, for this notation. And then we have plus 3 times the integral from -1 to 1 of h of x dx. And thankfully we have both of these integrals, the one for f and the one for h. For f it's 5, for h it's 7. So we get 10 plus 21, which is 31. Now for the last integral, we're given the integral from -1 to 4 of f of x dx. Now we know the area under this function from -1 to 1 is 5, and then from 1 to 4 it's -2. But we don't have anything that's from -1 to 4. So here's how we're going to use that area addition kind of property. What we can do is maybe just draw a quick picture right here. Here's -1, here's 1, here's 4 somewhere over here. So something like that. And we know that right here for from -1 to 1, we've got some area. And then from 1 to 4, it's got to be falling, the function has to be falling below the x-axis because we end up getting some negatively signed area overall. So there's more area below the curve than there is above the curve. So if we took the first area from -1 to 1 plus the second area from 1 to 4, then we should get the area from -1 to 4. Let's do that work right here. So this area from -1 to 4 is equal to the area from -1 to 1 plus the area from 1 to 4, which is 5 plus -2, which is 3. Again, by net area, we mean, by area, we're talking about net area here. Right, thank you so much for watching, and see you in the next video.